We're going to be using Newton's second law right here, along with the 5 equations of linear motion that we derived in the very first session. This is what problem 1 looks like. The girl has a mass of 30 kilograms, and her father is pulling her on a small surfboard, apparently. The acceleration is 0.4 meters per second squared. Problem is asking what is the force that the father is pulling with. So very simple, we just set up F equals ma, and then we substitute the mass in there, and we substitute the given acceleration, and you'll get an answer between 10 and 15 newtons. And to put that into perspective, a newton is approximately a quarter pound. So he's not pulling very hard, maybe only 3-4 pounds. So you could go further. You could ask yourself, how fast is she going after 1 second at this acceleration? She would be going 0.4 meters per second, not very fast. How about after 2 seconds? Same thing, just substitute into. Okay, now you're pushing a 601-pound snowmobile across a frozen river. You're pushing with a force of 20 pounds. So in order to use Newton's second law, we need to find the mass of the snowmobile. In order to do that, come over here and rearrange the second law in terms of mass. So it looks like this. The force being the weight of the snowmobile itself, and the acceleration, in this case, being the acceleration due to gravity. Now in the US system, the acceleration of gravity is 32 feet per second squared. In the metric system, as you know, it's 9.8 meters per second squared. So for this, you will get an answer between 18 and 20 slugs. A slug is the unit of mass in the US system. And then in order to figure out the acceleration of the snowmobile across the ice, come over here and rearrange the second law in terms of acceleration. And for the force, this time you'll plug in the force that you're pushing the snowmobile with. And now that we know the mass of the object you're trying to push, that'll be in slugs. And as long as you're using pounds and slugs, you'll get an answer for acceleration in feet per second squared. And your answer should be between about 1 and 1.5 feet per second squared for the acceleration. Now, just a quick reminder on the units. In the metric system in physics, we use what's called the MKS system. So we use meters, kilograms, and seconds. And as long as you're using meters, kilograms, not grams, and seconds for units, all the other units in these formulas will work out. You'll end up with newtons. And when we get to pressure, you'll end up with pascals. And when we get to energy, you'll end up with joules and so on. But it has to be meters, kilograms, and seconds. In the US system, you want to use feet for distance, slugs for mass, and seconds for time. And as long as you stick with those 3 units, you'll be okay. In order to answer this question, you will need to know Newton's 3 laws of motion. Here is a brief summary. Newton's first law of motion basically says if there's no force, there's no acceleration. Or putting it another way here, nothing starts moving or changes its velocity if it is already moving. In other words, speeds up or slows down, or changes its direction, because velocity is a vector, unless a force acts upon it. Now this force could be you pushing the snowmobile. That force could be gravity, pulling something down. Force could be wind, and so on. But basically, if there's no force, there's not going to be any acceleration. There's not going to be any change in velocity, in other words, of an object. And velocity involves both speed and direction. Newton's second law of motion. Quote, an object will accelerate in direct proportion to the force pushing it. So we put force up in the numerator because it's in direct proportion. And in inverse proportion to its mass. So we use mass in the denominator. And this is the way Newton actually expressed the second law. We usually rearrange it, F equals ma, but that is what Newton's second law is. Now, notice, if you're willing to accept Newton's second law, you don't need Newton's first law, because as you can see from F equals ma, you won't get any acceleration on an object unless there is a force. That's what this is saying. The second law is really a mathematical way of stating the first law. They are the same thing, basically. And lastly, the third law basically says that forces always exist in pairs. Or stated differently, forces do not exist in isolation. When a horse exerts a force on a cart, the cart exerts an equal and opposite force on the horse. If the horse has traction, the cart will move. But if the horse is standing on ice, the cart will never move, no matter how much struggling the horse does, because the cart is pulling back on the horse with an equal and opposite force. So if the horse is standing on dirt, why does the cart move? It's maybe pulling with 100 pounds. Well, the cart is pulling back with 100 pounds. So why does the cart move? Because the horse's hooves are pushing against the earth, and the earth then pushes back on the horse's hooves. So basically, if you look at the horse as the work engine standing in the middle, the earth is basically pushing the cart. You can think of it that way. So this question says you have to assume that there is friction between your boots and the ice, and so you need to choose which of the three laws pertains, and then explain why. Okay, here you're supposed to assume that with a full gas tank, your snowmobile weighs 640 pounds. What is its mass in slugs? So start by writing Newton's second law and rearrange it to solve for mass, and the force in this case is simply the weight of the snowmobile, and the acceleration is the acceleration due to gravity, feet per second squared. And so you'll get an answer here, between 15 and 30 slugs, let's say. So now you're supposed to figure out its weight on the moon, and the moon is going to have different acceleration due to gravity. The trick here is to realize that its mass hasn't changed. Its weight will change. It will weigh a lot less on the moon. But its mass, the number of molecules in the snowmobile hasn't changed, so its mass is going to stay the same. So its mass on the Earth is its weight on the Earth divided by the acceleration on Earth. And you could set up a similar equation for the moon, and then set the masses equal to each other. And so this relationship must be true. Its weight on the Earth divided by the acceleration due to gravity on the Earth has to equal the same ratio, its weight on the moon over the acceleration due to gravity on the moon. And you're trying to solve for this right here, the force or weight on the moon. You know the values of all the other three variables, so you can just substitute them in. And you're going to weight on the moon between, let's say, 100 and 120 pounds. Okay, this problem looks like this. You have a loaded sled. Apparently it weighs 750 pounds. So just draw an arrow pointing down with 750. You're pulling with a certain force, trying to figure out what that is. But you know there's going to be friction. And friction, we use a lowercase f, and we can point the arrow to the left because it's basically acting in opposition to your pulling force. So start by writing the second law. The sum of the forces acting on this object equals ma. Now fortunately, we don't even need to solve for the mass of the sled. All we need to know is the minimum force required to break it loose from the ice. So to have any acceleration at all, the sum of the forces over here have to be just above zero. So the pulling force, we can put a P there, minus the friction force, pulling it backwards as it were, has to be break even, has to be just over zero. Otherwise there would not be any acceleration. So we don't, again, fortunately, we don't need to go through and figure out what the mass is and what the acceleration would be and so forth. Now come over here. What is the frictional force? The frictional force of any object is the normal force clamping it down to the ice, as it were. In physics, normal does not mean the opposite of abnormal. In physics, normal means perpendicular, like this. So if the ice is flat, the normal force would be the force pushing down on the sled, which is just the weight of the sled in this case. If the ice was at a slant, and the weight was pulling this way, you would have to do a little bit of trigonometry to get the normal force, which would be pressing down perpendicular. But this is an easy problem. The ice is flat, so we don't even need to go through that. Now, what about the coefficient of friction? The static coefficient of friction we use when it's just getting started, because it takes a lot of force to bust it loose and get it to start moving. After that, we switch to the kinetic coefficient of friction, mu sub k, and you notice that's a smaller number because there is less friction once an object gets moving. So in this case, we're trying to break it. It says moving again from a dead stop. We're trying to break it loose. So we use mu sub s, the static coefficient of friction. And so you're going to get an answer 200 to 250 pounds for the friction over here, pulling it back, as it were. And so you can then say that the pulling force here has to be at least that amount. So the answer here is between about 200 and 250, and that's the answer to the problem, because your pulling force has to be at least that amount to break it loose and get it moving at all. In other words, pulling force has to be greater than the frictional force. So you could say the pulling force has to be greater than this amount here. Now the problem gets a little more complicated. Here you are pulling the 750-pound sled with the snowmobile, which itself weighs 640 pounds, and apparently you're able to pull with a force of 350 pounds, and there will be a frictional force over here on the left resisting the forward movement. So I draw an arrow pointing left, and I use a lowercase f for friction. First step is we're going to need to calculate the mass of the sled and the mass of the snowmobile. So we use the second law for that. We rearrange it in terms of mass, and we just substitute in the values for the weight and the acceleration due to gravity in the US system. And we end up with the mass of the sled, which is, I'm just looking at my notes here, between about 22 and 25 slugs here. And the mass of the snowmobile is 640 over 32, which is a nice rounded number. 20 slugs is the answer here. Next step is to calculate the frictional force over here. And we have to make some assumptions. We know there's going to be friction pulling that loaded sled across the ice. And in this case, we want to use the coefficient of kinetic friction, mu sub k, because it's already moving. The way the problem is worded, the sled is already moving down the ice. The question is, do we count any friction from the snowmobile? I'm going to say no, because we're given the force basically in the chain or in the cable going back to the sled, and so I'm assuming whatever friction might be in the front skids to that snowmobile is already taken into account. So I'm just going to account for the friction of the loaded sled. So write the equation for friction, this time using mu sub k, kinetic. The word kinetic means having to do with motion. And if I keyed that in correctly, I'm getting 105 pounds for friction. Now, if you think about it, it turns out that that is actually the answer to part B, because the only thing pulling back would be friction, and that's 105 pounds. So you would need to pull it with a minimum of 105 pounds. So now we're ready to solve for part A. What would be the acceleration of the cart? Start by writing the second law like this: the sum of the forces equals ma. And in this case, that's the pulling force minus the frictional force. So we're given the pulling force here. We calculated the friction force here. And the trick to a problem like this is realizing that for the mass term, we have to include the mass of both items, the snowmobile and the loaded sled, because both must be accelerated. Both have inertia, both have mass. And so any acceleration we're going to get out of this has to account for the mass of both of them. And so we calculated that over here. We calculated 20 slugs for the snowmobile, and I think I told you between 20 and 25 slugs for the sled. So you'll need to add those two together. So I'll put some of the masses in there for now. And that is what we're solving for. So in other words, take 350 minus 105, divide that by the sum of the masses of the two objects in slugs, and you will get the acceleration in feet per second squared. And if I did my math correctly, you should get between 5 and 6 feet per second squared for the acceleration. Here we are launching an arrow using a hunting bow at an angle of 15 degrees, and we're given the mass of the arrow and the acceleration of the arrow, and it's asking for the horizontal component of the force exerted by the bow on the arrow. Why? I don't know, because maybe further on down the problem you need to break that force into its x and y components. Pretty simple problem, involves a little bit of trigonometry, obviously. First, just figure out the force being applied at a 15-degree angle, the actual force. You'll need to convert mass into kilograms. Very important, otherwise it won't work. You won't get force in newtons. If you use grams, you got to use kilograms. And so you'll get an answer for the force at 15 degrees, somewhere between 140 and 150 newtons. After you do that, it's a fairly simple process to find the x component of that force. Just make this into a simple triangle with a hypotenuse of that amount, which I told you was between 140 and 150 newtons, right here, and write SO katoa, which stands for sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. And then ask yourself, oh, which one would give me my desired answer, sine, cosine, or tangent? In this case, cosine is the one you want to use, because we're trying to solve for that leg of the triangle right there. That's a 90 degree right there. We're trying to solve for that. So write cosine of 15 degrees equals adjacent over hypotenuse equals the force that we're trying to solve for, which is F sub x, divided by the force at 15 degrees, which you calculated up here, and rearrange it to look like this. Take your calculator, type in 15, hit the cosine button, multiply it by this force at 15 degrees, which you calculated here, and hit the equal button, and you'll get the force in newtons along the x-axis, or the x component of the force. And I'm getting an answer between 135 and 140 newtons, right in that range. Okay, you're test driving a Ferrari as part of a physics lab, and the mass of the car is given here, and it accelerates from 0 to 60 in 2.7 seconds, and 60 miles an hour is equivalent to 97 kilometers per hour. Calculate the magnitude of the net force that produces that acceleration. So you know you're going to need to use Newton's second law equation. You know the mass of the car, but you don't know the acceleration yet. So we need to go back to the 5 equations of motion and find one that will give us the acceleration. And looking at the 5 choices up at the top, that one is probably the easiest one to use. And so we want to rearrange it so we can solve for that, and we know that is 0, so we get that, and so we would have 97,000 meters. I'm converting kilometers over here to meters because it's easy, you just need to move the decimal point 3 places over. 97,000 meters per hour divided by the time, 2.7 seconds. Now we have to deal with the hour up in the numerator, so how many seconds are in an hour? The easiest way to go about that is to realize there's 60 seconds in a minute and 60 minutes in an hour. So there's 3,600. Now we want the hours on top over here, so it will cross out with that, leaving meters per second. You'll get a nice round number, almost exactly 10 meters per second squared. If you want to round it off to 10, that's fine with me. So the car is accelerating at that rate, and since you know the mass of the car, you can now figure out the force in newtons that's pushing the car. And that just simply looks like this, 1370 times 10. I'm sure you can handle that, and that will be expressed in newtons. So the engine, in other words, has to provide that much force in order to propel that car, having that mass, at that acceleration. Part B says calculate the distance in meters the car covers during that 2.7 seconds. Again, go to the top and choose one of the 5 equations of motion. There are a couple that will work. This one is one of them, and it's actually a very straightforward problem, and I will let you plug in the appropriate values and calculate it yourself. Your answer should be in the range of about 35 to 40 meters. And you'll note that's not very far. 35 to 40 meters is not a very long distance, and so the car is really getting up to speed quickly. Here's another uncharted planet type of problem. So you're venturing forth on an uncharted planet, and you throw a rock upward, and somehow you're able to measure its upward velocity, and you find that it returns back to the ground 1.61 seconds later. What does the rock weigh? You know you're going to use this equation. The weight of the rock is going to be the force. Okay, you're given the mass of the rock right there, and that's what you're trying to solve for. That's what you're going to need to know, the acceleration due to gravity on this planet. Notice the mass of the object, the rock or satellite or human or whatever it is, doesn't change from planet to planet in any of these problems. The mass stays the same. The rock has the same, number of atoms on Earth and on this uncharted planet. So the mass never changes. It's the acceleration and the weight, the F term, that always change from planet to planet. So this is what the diagram would look like, and we can just focus on one half of the trip. we know the round trip up and then down took 1.61 seconds. And so we can just focus on the trip up and ignore the trip down, and the problem will be a lot easier that way. So the trip up takes half of that amount of time. So what's 1/2 of 1.61 seconds? It's 0.805 seconds. So you know T2 there is 0.805. So with this information over here, you can easily calculate the rock's acceleration. It's just the change in velocity over time. And so substituting in for V2, that's 0. V1 is 14, and the time is 0.805. Now, it's important to keep track of your signage. I'm calling the upward velocity here positive. You could call it negative if you wanted. You'll just get the opposite sign for the acceleration. So as long as you're consistent, it doesn't matter which convention you use. You just need to keep track of it. And I'm getting between about 17 and 18 meters per second squared. And this is, when you think about it, this is the acceleration due to gravity on this planet. What else is causing it to decelerate? Nothing other than gravity, or ignoring wind, assuming the planet has an atmosphere. So now we have enough information to use Newton's second law to solve for the weight. So you can write F sub W if you want to represent weight. And for the mass, we're given that in the problem. And then for the acceleration, we want to plug in that value. You'll get a negative number for the weight. Don't let that throw you. I'm getting a number between about 100 and 110 newtons for the weight of the rock. Okay, if you have any questions about this homework, please let me know.